Hi, my name is Jamal, and I will be talking about our paper titled as Multi-Modal Contrastive Mask Autoencoders. It is a two-stage progressive pre-training approach for RGB datasets. This is a joint work with Umid at Intuitive Surgical. We've seen remarkable success of vision transformers in various computer vision tasks such as object classification, semantic segmentation. It attains excellent results compared to the state-of-the-art convolution networks in terms of efficiency and accuracy. In recent years, retraining vision transformers followed by fine-tuning also give rise to the state-of-the-art results for various computer vision tasks. More notable pre-training strategy is mask autoencoder, which has demonstrated to be very powerful, yet conceptually simple and efficient. Their pre-training objective is to mask out a high number of patches in an input image and to predict the missing region. Besides single model pre-training, there have been a recent surge in learning from multiple modalities. This has allowed us to develop large-scale pre-trained foundation models, which is of significant interest in computer vision because these models can be quickly transferred to many downstream tasks. For example, vision language-based training has improved visual representation for various tasks, even surpassing the state-of-the-art performance. For example, CLIP efficiently learns visual concepts from natural language supervision. Another method called contrastive captioners that train one image text foundation model with modified encoder-decoder architecture trained with both contrastive loss and the captioning loss. In this work, we are interested in leveraging a multi-modal data like RGB datasets. Various 3D understanding approaches have been leveraging RGB dataset for high-level understanding and low-level point matching tasks. One approach is to use contrastive learning to understand the correspondence between the different modalities. Recently, Pri3D explores to embed the 3D prior by leveraging multi-view RGB data to introduce geometric constraints in a contrastive learning scheme with resonant backbones. However, it relies on camera registration between multiple views for each frame, doesn't capture discriminative features beyond a mere cross-model correspondence. The second paradigm to leverage RGB dataset is again mask autoencoding. One particular approach is multi-MAE, which extends the vanilla MAE to multi-modal multitask setting and include depth modality and the segmentation modality. However, it requires both depth and semantic segmentation during the fine-tuning stage, and it also relies on the pseudo labels for the semantic segmentation. It also uses cross-attention mechanism to learn the cross-model relationship. Another approach is mask 3D, which effectively learns mask 3D priors from a single view RGB data frame by only reconstructing the mask or by only reconstructing the depth through masking out patches in RGB and depth modalities. However, this is very limited to the 2D image understanding, and it relies on MAE pre-training for any cross-model representation learning. We believe contrastive learning and mask autoencoders can be complementary to each other, as both provide unique data representation by extracting different discriminative features. However, it is not straightforward to combine them naively in a single framework. Recently, CoMAE proposed a single model self-supervised hybrid pre-training framework for small-scale RGB datasets. It incorporates contrastive learning and multi-modal mask autoencoding to pre-train a single encoder to capture cross-model representation. However, it requires both RGB and depth data during the fine-tuning as well as in evaluation. It is also limited to pre-training with a small-scale dataset, and it fails to distill any feature that has been learned in the stage 1, as stage 2 continues to pre-train the encoder using only the low-level pixel reconstruction tasks. Additionally, all these recent approaches frequently struggle to capture high-frequency components of the data, which further motivates us to explore alternative learning mechanisms. Recent advances in diffusion models have achieved remarkable success in image and video generation by leveraging denoising techniques, a strategy that has been absent in previous approaches, prompting us to investigate its potential in our context. So the question that we're trying to answer is that is there any pre-training approach that can combine powerful self-supervised methods for pre-training RGB data? So based on these previous limitations, we propose a two-stage progressive pre-training approach. Our approach is a very simple combination of contrastive learning, mask autoencoding, denoising used in diffusion models, and feature distillation. The goal is to learn representation from different learning mechanisms that can complement each other. In the stage one, to learn the correspondence between RGB and depth modalities, we use contrastive learning to discriminate the instances at patch level. We use info-NCE loss to pre-train the encoders with a fixed temperature. Indeed, an instance level contrastive learning can be used, but it would fail to capture local discriminative features across modalities as the tasks become easier by only learning high-level semantic. In the second stage, we further pre-train the encoder using mask image modeling. The goal is to understand the local spatial statistics of the input modality. Using the standard MAE approach, we mask out certain patches in both the modalities and enforce the model to reconstruct the mask patches. Unlike multi-MAE, we only reconstruct the mask patches of the depth modality. Empirically, we found that the reconstructing the patches of the RGB doesn't really improve the downstream performance. In the same second stage, we also introduced denoising. This has been shown a catalyst for modeling high-quality images and video generation. To further extract the high-frequency component, we apply denoising in this stage. We first add a Gaussian noise in the input. The noisy input is masked and then passed to the depth encoder. We then add the noise information to help separate the noise from the clean input. We treat it as a positional encoding and pass it to the simple linear layer to produce learnable embedding, which is then essentially added to the output of the encoder. These tokens are then concatenated with the RGB encoder representation and the learnable mask tokens. The concatenated result is passed to the decoder to predict the patches. The computation of the denoising doesn't bring any overhead to the pre-training compared to the vanilla MAE, since we use a lightweight MLP and compute the loss on the reconstructed unmasked patches. Because the decoder also reconstructs the unmasked patches, which can go wasted in the vanilla MAE pre-training. To distill the global modality-specific embedding in the second stage, we use the output of the encoder as a visual embedding for each of the modality. We then apply the max pooling to output a global embedding. Afterward, we align this second stage global embedding to the global visual embedding from the first stage model using the smooth L1 loss. To verify the effectiveness of our approach, we use the pre-trained encoder to flexibly transfer using RGB modality for multiple downstream tasks such as semantic segmentation, depth estimation, and instance segmentation. We first present the results for semantic segmentation on the scanned dataset. From the table, you can see the performance of our approach and other approaches. And our approach outperforms both MaskR 3D and other sort of approaches that level RGBD during the pre-training. We also demonstrate the effectiveness of our approach on 2D instance segmentation. We use ScanNet for comparison against other baseline and use MaskR CNN as the instance segmentation head on the top of the VIT encoder. We see the same observation that our approach transfers the learned representation better by outperforming the state-of-the-art approaches. In this experiment, we studied the efficacy of our pre-trained model for depth estimation task. We use NYU-V2 for this downstream task and reported delta 1 on the test set. We use DPT as dense prediction head, following multi-MAE for all the approaches. We can draw the same observation from the table that our approach outperforms the state-of-the-art approaches. We also show the data efficient nature of our pre-training strategy by fine-tuning it in a limited label data scenario. Our approach consistently outperformed Mask 3D, MAE, and Pry 3D across different ranges of limited label data. Here we want to highlight the importance of using different self-supervised framework. It shows that the contrastive learning alone can perform reasonably well. By pre-training using only depth reconstruction loss in the second stage, the performance jumps significantly, while integrating all the objectives in the second stage significantly enhances the final performance. Without our feature distillation, the performance actually drops at 0.5 MIU in total. In the second figure, you can see the effect of stage 1 pre-training on the ScanNet. Without having stage 1, our stage 2 can still be able to actually learn much better representation as compared to RGB plus depth mask autoencoding. This table shows the performance of different component of denoising loss on ScanNet 2D segmentation. By simply adding the noise in the input, the performance actually improves by 0.4 MIU. The figure on the right side shows the ScanNet semantic segmentation performance. Based on the maximum noise level, the best performing model was achieved with 0.05 value. And the model performance doesn't really drop even if we increase the amount of the maximum noise. To conclude, we proposed a simple and effective multi-modal pre-training to integrate strong self-supervised methods. We train our model without any semantic pseudo labels. We, inspired by diffusion models, we integrate denoising to extract high frequency component. We also integrate feature distillation to distill knowledge learned in the second stage. And finally, we actually see a notable performance gains on multiple data sets for multiple downstream tasks. And that's what we have. Thank you for your attention. For more details and more experiments results, please visit our paper